Let's now discuss why are threads useful. We will do that by looking at an example on a multiprocessor or a multi-core system. At any given point of time, when running a single process, there may be multiple threads belonging to the process, each running concurrently on a different processor. One possibility is that each thread executes the same code but for a different subset of the input, for instance, for a different portion of input array or an input matrix. For instance, T1 processes this portion of the input matrix, T2 processes the next one, and so forth. Now, although the threads execute the exact same code, they're not necessarily executing the exact same instruction at a single point in time. So every single one of them will still need to have its own private copy of the stack, registers, program counters, etc. By parallelizing the program in this manner, we achieve speed up. We can process the input much faster than if only a single thread on a single CPU had to process the entire matrix. Next, threads may execute completely different portions of the program. For instance, you may designate certain threads for certain input-output tasks like input processing or display rendering. Or another option is to have different threads operate on different portions of the code that correspond to specific functions. For instance, in a large web service application, different threads can handle different types of customer requests. By specializing different threads to run different tasks or different portions of the program, we can differentiate how we manage those threads. So for instance, we can give higher priority to those threads that handle more important tasks or more important customers. Another important benefit of partitioning what exactly are the operations executed by each thread and on each CPU comes from the fact that performance is dependent on how much state can be present in the processor cache. In this picture, each thread running on a different processor has access to its own processor cache. If the thread repeatedly executes a smaller portion of the code, so just one task, more of that state and of that program will be actually present in the cache. So one benefit from specialization is that we end up executing with a hotter cache, and that translates to gains in performance. You may ask, why not just write a multi-process application where every single processor runs a separate process? If we do that, since the processes do not share an address space, we have to allocate for every single one of these contexts address space and execution context. So the memory requirements, if this were a multi-process implementation, would be that we have to have 4 address space allocations and 4 execution context allocations. A multi-threaded implementation results in threads sharing an address space, so we don't need to allocate memory for all of the address space information for these remaining execution contexts. This implies that a multi-threaded application is more memory efficient, it has lower memory requirements than its multi-process alternative. As a result of that, the application is more likely to fit in memory and not require as many swaps from disk compared to a multi-process alternative. Another issue is that communicating data, passing data among processes or synchronizing among processes requires inter-process communication mechanisms that are more costly. As we'll see later in this lecture, communication and synchronization among threads in a single process is performed via shared variables in that same process address space, so does not require that same kind of costly inter-process communication. In summary, multi-threaded programs are more efficient in their resource requirements than multi-process programs and incur lower overheads for their inter-thread communication than the corresponding inter-process alternatives.